Hi everyone. Before we start the lesson for today, we have to go over something important, which is how to sketch angles that are greater than 360 and also how to sketch negative angles. So our learning goal for this warm-up is to learn to sketch angles that are greater than 360 and negative angles. So the question says, sketch each angle theta in standard position. Include the principal angle, which you're going to label P dot A dot, and alpha, which we already know what alpha is, in your sketch. Okay, so I'm going to go through this, hopefully. So I'm going to draw a little XY axis here. And if we remember from angles and quadrants in the Castrol, this represented 0 degrees, and then 90 degrees, and 180 degrees. So each quadrant's 90, 270, and then 360. So what happens if we have an angle that's bigger than 360, like 510? We want to know, where should we draw that? So if we think about, if we keep going in a chunk of 90, we could do 360 plus 90. So up at the top again, so if we go all the way around once and then back to the y-axis, that's going to be 450 degrees. And then 510 is more than 450. And if we added another 90, we would be at 540 over here. So we know 510 is 30 degrees less than 540. And remember, in each quadrant, like the 45 degree mark is the halfway. So when you draw one of these angles, you don't want to use a protractor. You just want to make sure that it's in the right quadrant. So again, this was quadrant 1, quadrant 2, quadrant 3, and quadrant 4. And then either closer to the y-axis, closer to the x-axis, or right in the middle, okay? And that will depend on where it is in the quadrant. So if I was trying to draw this one, the first thing I would do is I would do 510 degrees minus 360 degrees. So I'd take it 510 minus 360. So that says 150 degrees. So if I pretended I was just going to draw 150 degrees, I would know it was going to be in quadrant 2, and I would know it was going to be closer to the x-axis, because 150 is only 30 degrees from 180. Okay, so if I want to draw 510 in standard position, then I'm going to go all the way around once, that's 360, and then back again. So this is theta, which in our case is 510 degrees. Okay, so sketch each angle theta in standard position. Include the principal angle and alpha. So let's do alpha first. So alpha doesn't need an arrow. Alpha is going to be the angle between the terminal arm and the x-axis, and it'll always be the angle between the terminal arm and the x-axis. So we figured out that the correct place to draw this was at 150 degrees from 0, and which makes alpha 180 minus 150, or 30 degrees. So there's alpha. Now what's this principal angle? So that's a new term that we haven't used yet. The principal angle is the positive angle with the same terminal arm, but is, but is between 0 and 360 degrees. Okay, so the principal angle of this one is 150. So 510 minus 160 was 150. So that is the angle between 0 and 360 that has the same terminal arm as 510. So I'm going to draw it in a different color. So this green angle, and this does have an arrow, is my principal angle. Okay, so there's three angles drawn on here. So 510, 360 plus 150 is 510. Then I've got alpha, which is the little angle, we call it the related acute angle, which fits in between the x-axis and the terminal arm, 30 degrees in this case. And then we've got the principal angle, which is the angle that has the same terminal arm as 510, but is always between 0 and 360. So it's always a positive angle between 0 and 360. All right, so the next angle we want to draw is 585 degrees. So I'm going to draw an XY axis again. So 585 degrees. So the first thing I would do is subtract. It's bigger than 360, so I'm going to subtract 360 to see if I can figure out which quadrant it should be along in now. So 585 subtract 360 is 225. So that does fit between 0 and 360. So remember, this represents 0, 90, 180, 270, back to 360. So we can see that it's going to be between 180 and 270. And then is it going to be closer to the x, closer to the y-axis, or right in the middle? Well, let's see. So let's try 270 minus 225. That's 45 degrees. So that means it's 45 degrees away from 270. So it means it's going to be right in the middle, the terminal arm. So we're trying to make it look right in the middle. So 585 is going to be, so here's starting at 0, all the way around once is 360. So there's to 360, and then 225 more puts me to here. So there's theta. Theta is 585 degrees. Now alpha is always between, so it doesn't have an arrow on it, it's always between the x-axis, which is here, and the terminal arm, which is here. So we figured out that this was 45, but that's not alpha, but there's 90 degrees in a quadrant, so alpha is also 45 degrees in this case. Okay. And then the last thing we want to add on is our principal angle, which starts at 0 and goes around to the terminal arm, and we can use P dot A dot, and that's our 225 degrees. So it's actually got the same terminal arm as 585, but it fits just between 0 and 360. So that's our principal angle. Okay, so we've just looked at how to draw two angles that are larger than 360 in what we call standard form. And so that involves going all the way around once and then over to where it would be between 0 and 360. All right, now we're going to try a negative angle. Some of you might be able to guess what a negative angle would work like, but I will show it all out for you here. So again, we're going to start off with our x-axis and our y-axis, and this is 0 degrees. Now, instead of going from quadrant 1, 2, 3, 4, for a negative angle, we go in the reverse direction. So this is negative 90 degrees down at the bottom here. This would be negative 180 degrees, negative 270 degrees, and then back to negative 360 degrees. So negative 120 degrees, we can see, is going to be in our quadrant 3. And 120 is 30 more than 90, so it's going to be closer to the y-axis in this case. So we'll draw our terminal arm so it looks like it's closer to the y-axis. And then, so negative 120 degrees is going to be, so instead of going counterclockwise, we're going to go clockwise with an arrow. And this is theta, which is negative 120 degrees. Now alpha is always between the x-axis and the terminal arm, so alpha is going to be in there. So again, we said that the 120 was 30 more than 90, which means that alpha is going to be 60 degrees, because 90 degrees make up a quadrant. Okay. Now the principal angle always has to be positive, and it has to be between 0 and 360. So it's got to have the same terminal arm, but it's got to start at 0. It's got to be positive. So there's our principal angle. And I can reason it through. It's going to be 180 plus 60, just adding alpha, which gives me 240 degrees. Or you could think of, since negative 120 is less than, or is a negative number, instead of subtracting 360 like we did with our angles that were bigger than 360, we could add 360. Because when you add 360, you get right back around to where you started from. So negative 120 plus 360 gives you 240. And that would be a way of knowing where to draw your terminal arm as well. Okay, so you draw your terminal arm at 240, which is between positive 180 and positive 270, closer to the 270. Okay, so that would have been another way we could have done it, but then we would have had to remember to draw our arrow going in the reverse direction for a negative angle. All right, another one to try here. Okay, so negative 570. So again, we know we've got 0, negative 90, negative 180, negative 270, negative 360, and then add negative 90 more and you get negative 450, negative 90 more, 540, negative 630. So we know it's going to be in this quadrant somewhere. But how we can figure that out? Well, we can take our negative 570 and add 360. Negative 570, add 360. And that still puts us in the negatives. So then we could add 360 again, which tells us that our terminal arm should be located at 150 degrees. Okay, so where would 150 degrees be? We know 0, 90, 180, so 30 degrees less than 180, which is closer to the x-axis. So negative 570 is going to be all the way around in the negatives one time. So there's negative 360, negative 450, negative 540, negative 570. So there's theta. So theta is this looping angle here, negative 570 degrees with the arrow. Alpha is always the angle between the terminal arm in the x-axis, and it's always positive, so alpha in our case is going to be, this is 150 and 180, 30 degrees. And then the principal angle is always the positive angle between 0 and 360 that has the same terminal arm. So this would be my principal angle, and it would turn out to be 150 degrees. So again, an important thing to know here is that 150 degrees and negative 570 degrees have the same terminal arm. Okay, so that's an important thing to remember as we're going to move on later when we start the new lesson. Okay, so we'll do a couple more of these. So 1020, it's a positive angle. So we've got our x and y axis. And we know that one time around is 360, so I'm going to subtract 360. 1020 minus 360, 660. So I'm still not between 0 and 360, so I'm going to subtract 360 again. I guess these aren't equal. Minus 360 again. $300. So now we've figured out the terminal arm should be drawn at 300 degrees. So again, this is 0, 90, 180, 270, 360. And 300 is going to be 60 less than 300, and 60 is less than halfway, so it's going to be closer to the y-axis. So that's where our terminal arm should be in quadrant 4. But we had to subtract 360 twice, so we've got to go all the way around once, 360, 720, all the way around a second time, and then all the way around 300 degrees more to get to 1020. So here's theta equals 1020 degrees. Now we want to put alpha in. So alpha is always between the terminal arm and the x-axis without an arrow. And we figured out that 300 is here. So there'd be 30 degrees in here between 270 and 300, but 60 degrees between the terminal arm and the x-axis. And then finally we need the principal angle, which always starts at 0, goes counterclockwise around to the terminal arm, and we'll use P dot A dot is 300 degrees. Negative 300 degrees. So again, 0, negatives, negative 90, negative 180, negative 270, negative 360. So we can see that negative 300 is going to be in quadrant 1 this time, and closer to the y-axis. So there's our terminal arm. And we want to show a negative angle, so we start at 0 and we go clockwise. So that's going to be theta is negative 300 degrees. Then we need alpha in here, which is the distance between the terminal arm and the x-axis, sorry, so that's 60 degrees, which is also the same as the principal angle, but the principal angle has an arrow. So the principal angle is also 60 degrees, but it's directed. All right, and our last example before we move on to the main lesson today, 690 degrees. So being able to draw angles that are larger than 360 and negative angles is going to be part of what we need to know for today's lesson. So 690, I'm going to subtract 360 right away. 690 minus 360 is 330, so that fits in between 0 and 360, so it's going to be quadrant 4 and closer to the x-axis, because that's only 30 degrees away. 45 is the middle. So for 690, I go all the way around once, which is 360, and then all the way back to here, 330. So this is my theta equals 690. Then I need alpha on here, which is between the x-axis and the terminal arm. And we said that when we were drawing 330, we were locating our terminal arm at 330, which was 30 degrees away from 360, so there's alpha. And then our principal angle starts at 0, goes around to the terminal arm. Principal angle always has to be positive between 0 and 360, so it's 330 degrees. Okay, so there's our warm-up on how to draw positive angles that are bigger than 360, and also how to draw negative angles in standard position. All right, so our lesson today is on the special triangles. So we're learning to use the special triangles to find exact trigonometric values. So this is really important for grade 12 advanced functions. The angles 30, 45, and 60 degrees, and their related angles in the other quadrants, are benchmark angles that are used frequently in the study of trigonometry. For this reason, it's important for mathematicians to know and memorize their associated trig values. So first we're going to look at the 45-degree special triangle. So if we look at the 45-degree special triangle, you can notice that in the xy axis, it's halfway between 0 and 90, which makes sense, okay? And we're going to imagine that it's got an r value that's equal to 1, okay? So our radius of 1. And we've made it a 45-degree angle. So here's our terminal arm. There would be the point on the outer edge. The terminal arm could extend, but there's our point, okay? And this length for r is 1. Now, and then if we want this point here, figure out what it is, then we would draw down and make our triangle with the x-axis, a right angle triangle. But if this is 45 degrees and there's 180 in a triangle, then this angle up here is also 45 degrees, which makes this a special kind of triangle. It makes it an isosceles triangle, which means these two sides are both the same length, okay? In an isosceles triangle, the sides opposite the opposite angles are the same length, okay? So if this is x, then this length is also going to be x. And we can use our r squared equals x squared plus y squared to figure out what that length x is, and it's going to be the same for y. So we know r is 1, and we don't know x squared, but we know y is going to be the same as x because it's an isosceles triangle. So on this side now we can collect these because they're like. So we have 2x squared, and now we can use reverse BEDMAS to solve for x. So if we're using reverse BEDMAS, we would divide both sides by 2 first, and then square root. And we're in the first quadrant, so I'm not going to worry about the plus or minus, but we can do the root of 1 over the root of 2. And so our x is, the square root of 1 is 1, but the square root of 2 is yucky, so we're just going to leave it as square root 2. So that means this distance from 0 to where this right triangle would end is 1 over root 2. And now I can call this y, but we know it's going to also be positive 1 over root 2. So this point here is going to be 1 over root 2 1 over root 2 to get to that point there on the terminal arm. Okay, so again, so that's how we've got our three sides, x, y, and r. Now we can get sine, cos, and tan. So the sine of 45 degrees, and we're looking for exact values rather than our calculator. So I'll go through that in a second. But the sine of 45 is going to be the y value, which is 1 over root 2, over the r value, which is 1. When you divide something by 1, you just get the same. So the sine of 45 degrees is 1 over root 2. And that's the exact value, no decimal approximation. So let's show that that's true. So make sure your calculator is in degrees. And we want to do the sine of 45 degrees. And it tells me on my calculator 0.707106781. So let's see if 1 divided by root 2 gives me that same decimal. 1 divided by the square root of 2 equals 0.707106781. So this is the exact value of the sine of 45 degrees. Okay, and then the cosine of 45 degrees is the x value, 1 over root 2, over the r value, which is 1. So the cos of 45 is also, the exact value is also 1 over root 2. So no approximately 0.7, we're giving the exact value. Okay, exact values are kind of an important theme in grade 11 math. And then the tangent of 45 degrees is equal to the y value, which is 1 over root 2, divided by the x value, which is also 1 over root 2. And you can see that you're dividing a number by itself. So whenever you divide a number by itself, you get 1. So the sine of 45 degrees is exactly 1 over the square root of 2. The cos of 45 degrees is exactly 1 over the square root of 2, and the tangent of 45 degrees is exactly 1. Okay, so that's our first special triangle, the 45-degree triangle. Now we're going to look at our second special triangle, which is our 60-degree triangle. So again, our r value is 1. R is 1. And so what we're going to do is we're going to imagine that we've created an isosceles triangle, because this distance from here to here, it shows you on here, is also 1. So this is just going to help us get. So what we really want is we want to know what this value is. So this would be our x value. And then what this value is, this height, which will be our y value. Okay, but if we think of this as an isosceles triangle right now, where this is 1 and this is 1 and this is 1, all these angles being 60 degrees, then if we drop down our perpendicular and split this in half, then this 1 gets split in half. So we can just logically say that the x value is 1/2. So now we know r and x, but we don't know what y is. So we can use, so if we're looking at this right triangle here, we've got the Pythagorean theorem again. So r is 1. X, we reasoned, was going to be 1/2. And y, we're going to figure out. So we square 1 squared and we get, 1. Square 1/2 and we get 1/4. Subtract 1/4 on both sides. So 1 minus 1/4, a lot of people would just know that's 3/4. Some people might want to change 1 to 4/4 and get a common denominator if you aren't comfortable just doing it in your head. And now we want a square root. So again, we can do this idea of square root of 3 over square root of 4. So we would get that our y value, square root of 3 is not a nice number, so we're going to leave it, but square root of 4 is 2. So that means this y value, so this distance here would be the square root of 3 divided by 2. Square root of 3 divided by 2. Okay, and it looks like that square root of 3 divided by 2 is larger than 1/2. We know 1/2 is 0.5, so let's just try square root of 3 divided by 2 is about 0.866. So you can tell that that's correct. This should be bigger than 1/2. Okay, so now let's look at our exact values of the sine of 60 degrees. So the sine of 60 degrees is the y value, which we just figured out was root 3 over 2 over the r value, which is 1. So if we remember these from the CAST rule, sine of theta is y over r. Cos of theta is x over r. And tan of theta is y over x. But r is 1, and dividing by 1 doesn't change anything. So in this case, the sine of 60 is just going to be root 3 over 2. Because root 3 over 2 divided by 1 is still root 3 over 2. And the cosine of 60 is the x value, which is 1/2, divided by 1, which is still just 1/2. But tan, a little trickier here, the tangent of 60 degrees is the y value, which is root 3 over 2, divided by the x value, which is 1/2. Okay, so then you have to remember how to divide fractions, which is multiplying by the reciprocal. So if you multiply the tops together, root 3 times 2 is 2 root 3. 2 times 1 is 2. The 2's divide out, and we get root 3 for the tan of 60. Just something that you probably haven't remembered since elementary school, but when you divide fractions that have the same denominators, the denominators divide out, just like they did here, but we didn't show the work. So we can actually say tan 60, if it's root 3 over 2 over 1/2, and the denominators are both exactly the same, we can mentally divide them out, and we'd be left with root 3 over 1, which is just root 3. And I just feel like that's a nice, easy way to do it. So here we have that the sine of 60 is root 3 over 2, the cos of 60 is 1 over 2, and the tan of 60 is just root 3. Okay, our third special triangle is fairly straightforward because it's just the 60-degree triangle turned on its side so that the 30 is down here and the 60 is up here. And so if you remember the 60-degree triangle that we just looked at, it had the exact same three angles, 60, 30, and 90. So between the 60 and 90, the length was 1/2 when r was 1. And between the 90 and 30, the length was root 3 over 2. So if we just apply that here, between the 30 and 90, the length was root 3 over 2. And between the 90 and 60, the length was 1/2. So that makes this point here, when r is 1, so here's our x and our y, over root 3 over 2 and up 1/2. So now we can just figure out the sine, cos, and tan again. So the sine of 30 degrees is the y value over the r value, but the r value is still 1, so the sine of 30 degrees is 1/2. The cosine of 30 degrees is the x value over 1, because the r value is 1 again, which is root 3 over 2. And the tan of 30 degrees is the y value, which is 1/2, over the x value, which is root 3 over 2. And we can use that new handy thing where the denominators are both the same when we're dividing out, so they divide out. And we're left with 1 over the square root of 3. 1 over the square root of 3 for tan. So we've got the sine of 30 is 1/2, the cos of 30 is root 3 over 2, and the tan of 30 is 1 over root 3. So those are our three special triangles, 45, 60, and 30, or 30, 45, and 60. So now we're going to learn how to use those special triangle values along with the CAST rule to determine the exact value of different trig functions. So the cosine of 120, we want the exact value of the cosine of 120. So without using your calculator, and we'll use our calculator after to look at the answer, but without using a calculator, find the exact value of the cosine of 120. So first thing we want to do is draw 120 degrees in standard position. So there's lots of things I have to remember in a question like this. All right, so first thing I have to remember is there's 4 quadrants, 0, 90, 180, positive, 270, 360. And I want to know, where does 120 fit? So here's 90, here's 180. 180 minus 120 is 60. Or we know that 120 is 30 more than 90, so the 120 should be drawn so that it looks closer to the y-axis. So here's 120 degrees. What we are interested in, though, is what's alpha? Alpha is the related angle that's related to 120. And in our case, alpha is the distance, again, between the x-axis and the terminal arm, so it's 60 degrees. Okay? So far we've drawn our angle in standard position, and we figured out what we call this alpha, the related acute angle is. So our answer for cos of 120 is going to be related to cosine of 60. Okay? So we've just changed this 60-degree special triangle. We flipped it over and we've put it over in this quadrant here. So it's going to have this side being a half again, this side, or a negative a half because it's on the negative side of 0, 0. Our y value is still going to be positive root 3 over 2 to get up here, and then our r value is still going to be 1. So that's kind of the thinking behind it. All right, so alpha is 60, but rather than just turning around those triangles all the time, we can use the CAST rule. So the CAST rule tells us where, in this case, cos is positive. So cos is going to be positive here and here, which means it's going to be negative here and here. So we're in a quadrant where the cosine is negative. Okay? So the cos of 120 is going to be negative cosine of the related angle, which is 60 degrees. So it's going to be negative, and what was the cos of 60? 1/2. And then if you type in cos 20 on your calculator, sorry, cos of 120 on your calculator, if you're in degrees, you should get negative 0.5 or negative 1/2. Okay. So that's how you would write out your answer, and this is the work that you would need to show. All right, next one. Sine of 315 degrees. So again, we know this is 0, 90, 180, 270, 360. So 315. So I know it's going to be in quadrant 4 here. And if I do 360 minus 315, I get 45 degrees. So that means it's going to be halfway in here. Let's try to make it look halfway. So this is my 315 degrees. But alpha is the angle between the terminal arm and the x-axis is going to be 45 degrees, which means that the sine of 315 is going to be related to, not exactly the same, but it's going to be related to the sine of 45 degrees according to the cast rule. So we're looking at sine. Sine is positive here and here, which means it's going to be negative in these two quadrants. So the sine of 315 is going to be negative sine of 45 degrees. So negative because sine's negative in the fourth quadrant, and 45 because the related angle is 45 degrees. And that's negative. Well, what was the sine of 45 degrees? So that was our first special triangle. So if you look at it here, the sine of 45 degrees was 1 over the square root of 2. It's our isosceles triangle. So negative 1 over square root of 2. So again, check on your calculator. So the sine of 315 degrees gives you negative 0.707106781. And let's try just doing what we got our exact value. So negative 1 divided by the square root of 2. Also, you get negative 0.707106. Okay? But this is exact, not a rounded decimal. Okay? So that's what exact value means. Okay, moving on. Sine of 600 degrees. Okay, so we're getting trickier here. So the sine of 600 degrees is going to be, it's going to have the same sign as we'll figure out where to draw it first. So 600 minus 360 is 240 degrees. So again, we know like 0, 90, 180, 270, 360. So 600 minus 360 was 240 degrees. So they have the same terminal arm, which means they're going to have the same sine, cos, and tan. So sine of 600 is going to be the same as the sine of 240 degrees. So 240 degrees, we know fits in here between 180 and 270. So 270 minus 240 is 30, which means it's closer to the 270 because 45 is the halfway point. So if I was drawing 600, I know I would have to go all the way around once and then back again. And I also know that that's to 240. But alpha is what I'm concerned about. So if this part in here was 30, then this is 60. So then I'm going to use the cast rule. So according to the cast rule, sine is positive in the second quadrant and the first quadrant and negative here and here. So now we can say it's going to be the same as the negative sine of 60 degrees. But then I have to remember, what was the sine of 60 degrees? We're looking for that paper here. Sine of 60 degrees is positive root 3 over 2. So our answer is going to be negative, and then the sine of 60 is root 3 over 2. Okay, again, let's prove that on our calculator. So the sine of 600 degrees is negative 0.866025, And then we should get that same decimal if we do negative square root of 3 divided by 2. Same. Okay. Tan of 150. So 150, this is 0, 90, 180. So 150 is going to be closer to the x-axis. So that's 150 degrees. And alpha is going to be 30 degrees. So the tan of 150 is going to be related to the tan of 30 according to the CAST rule, which says that tan is positive in the first quadrant and the third quadrant and negative in the second quadrant. So the tan of 150 is going to be negative tan of 30 degrees. So it's going to be negative, and then the tan of 30 degrees was 1 over root 3. Tan of 30 was 1 over root 3. So it should be negative 1 over the square root of 3. Okay, so again, let's try those. So the tangent of 150 is negative 0.57735. And then let's try negative 1 divided by the square root of 3, negative 0.57735. Okay, and again, this is exact. And that's why we're spending this time doing it this way, to get the exact value without using a calculator. Okay, so now we're going to look at cosecant. Okay, so when I get one like cosecant, I'm going to reserve my answer, and I'm going to look at, first of all, I want to look at what ratio is cosecant related to. It's related to sine. So if I knew what the sine of 210 degrees was, then I could flip it upside down and I would know the cosecant. Okay? So much like, here I'll just use a piece of scrap paper when we were doing our CAST rule question. If we were given like the cosecant of theta was equal to 5 over 3, then to use the CAST rule, we would change that to the sine of theta is 3 over 5. Okay? So we're going to use that same kind of idea for finding exact values. So we're just going to leave some room up here to put our final answer in, but we're going to focus on the sine of 210 for now. So we're going to draw our xy axis. So, and we know this is 0, 90, 180, 270, and 360. So 210 is in the third quadrant closer to the x-axis. So here's 210 degrees, and alpha is going to be 210 minus 180, which is 30 degrees. Okay, and then we're looking at sine right now. So according to the CAST rule, sine is positive here and here, and negative in the third quadrant where we're looking at. So sine of 210 is going to be negative sine of 30, which is negative, and then the sine of 30 is a half. So since the sine of 210 is negative 1/2, that means the cosecant of 210 is going to be negative 1/2 flipped upside down, which is negative 2 over 1, or just negative 2. Okay? So the cosecant of 210 is negative 2. Now there isn't a cosecant button on your calculator, but we can do 1, since they're reciprocals, 1 divided by the sine of 210. That would be the same as the cosecant of 210. So negative 2, which is what we got. All right, the secant of 240. So again, we'll leave some space up here. Now secant's related to cosine. So we're gonna find the cosine of 240 and then flip it upside down to get the secant. Okay, so the cosine of 240, so 0, 90, 180, 270, 360. 240 is going to be in the third quadrant closer to the y-axis because 240 is only 30 degrees away from 270. So here's our 240 degrees. But alpha is going to be 60 degrees. So 240 minus 180 is 60. Alpha is always between the x-axis and the terminal arm. Sorry. Okay, so Castrol, C-A-S-T, we're looking at cos is positive here and here, so it's going to be negative. So it's going to be negative cos of the related angle, which is 60 degrees. Cos of 60 degrees, if you look at our special triangle here, is 1/2 again. Cos of 60 is 1/2, negative 1/2. And then we need to flip that to get the sec. So the sec of 240 should be -2. Again, so if we tried that on our calculator, we don't have a sec button, so we would have to do 1 divided by the cosine of 240, which is -2. So that's our strategy. Okay, cotangent of 840 degrees. So first of all, we want to figure out, well, actually we can go down here. So what's related to cotangent is tangent, so we want to focus on the tangent of 840 degrees. When we're drawing our picture. So the tangent of 840 degrees. So where is 840 going to be? So we could keep going by 90s. But I'm going to start off and I'm going to do 840 minus 360. 840 minus 360 is 480. Subtract 360 again. So it's going to be at the same location as 120 is going to be. And 120, we know 0, 90, 180 is going to be here. Oops, should look closer to the y-axis. There we go. So 840 we know is going to be all the way around once is 360, all the way around twice is 720, and then over here to 120 degrees more to 840. And then alpha is going to be, this was 120. So and this is 180. So alpha is going to be 60 degrees. So the tan of 840 is going to be the same as the tan of 120 degrees. Because they both have the same terminal arm. Now let's use the cast rule. So the cast rule says that tan is positive in the third quadrant and the first quadrant and negative in these two quadrants. So it's going to be negative tangent of 60 degrees. And then we can look up what was the tangent of 60 degrees. It ended up being √3. So negative root 3 is the tangent of 840. But now we know we have to flip that upside down to get the cotangent of 840. So the cotangent of 840 is going to be negative 1 over root 3. Okay, so then let's try our calculator out. So cotangent of 840, so we're going to do 1 divided by the tangent of 840. Gives me negative 0.57735. And then let's try negative 1 divided by the square root of 3, negative 0.57735. Okay? So we got the exact value without a decimal approximation. All right, the cosine of negative 225 degrees. So again, angles that have the exact same terminal arm have all the exact same trig values. So angles that have the exact same terminal arm. So for instance, the angle 840 is going to have the same sine, cos, and tan as the angle 120 because they have the same terminal arm in the exact same position. So if I was doing one like this, I would know that the cos of negative 225, so again, remember from our warm-up, this would be like negative 90, negative 180, negative 270, negative 360. Negative 225 is going to be in quadrant 2, and if I do 270 minus 225, I get 45 degrees, so it's going to be right in the middle. Hopefully that looks in the middle-ish. So here is negative 225 degrees. Negative 225 degrees has the same terminal arm as this angle here, which is, this is alpha's 45 degrees here. 90 plus 45 is 135 degrees. So without drawing a picture, I could get that 135 by saying to myself, okay, negative 225, I want to get a positive angle that has the same terminal arm. So if I'm at negative 225, I want a positive angle that has the same terminal arm. So if I backtrack 360 degrees, or I add positive 360 degrees, I'm going to get to the exact same spot because there's always 360 degrees in a circle. And if you add those, that's how you get the 135. Okay, so the cos of negative 225 is going to be the same as the cos of 135 because they have the same terminal arm. So they're going to have the same sine, cos, and tan. So now I have to apply the cast rule again and special triangles. So I know my special triangle is my 45-degree triangle. And I know cos is positive here and here and negative in the second quadrant, which is where my angle is. So it's going to be negative cosine of 45 degrees. So then if I look up the cosine of 45 degrees, which is here, it was 1 over root 2, cosine of 45 degrees. So negative 1 over root 2. Okay, and again, we can compare. So cosine of, I'm going to use brackets because it's a negative, negative 225 is negative 0.707106, and negative 1 divided by the square root of 2, same thing. Okay? All right, cosecant of 300. So we'll leave some space and we'll first find the related sine of 300 degrees. So 300 degrees, this is 270 and this is 360. So 300 is going to be closer to the y-axis. So here's 300 degrees, which means alpha is going to be 60 degrees. Remember, alpha is always between the x-axis and the terminal arm, not the y. So the sine of 300 is going to be, so according to the CAST rule, sine is positive up here and negative down here. So it's going to be negative sine of 60 degrees, the related angle, which is negative. So the sine of 60, root 3 over 2. You haven't, sine of 60 is root 3 over 2. It's going to be negative root 3 over 2. But that means that the cosecant of 300, got to flip that upside down, is going to be negative 2 over root 3. Okay, and then let's check that on our calculator. So we want to do, for cosecant, we would do 1 divided by the sine of 300, negative 1.1547. And then let's try negative 2 divided by the square root of 3, also negative 1.1547, etc. Okay, so there's the exact value of the cosecant of 300 degrees. And then our last example, the secant of negative 690. So I want to know where to draw negative 690, so I might add 360. So negative 690's got the same terminal arm as, so negative 690 plus 360. So it's going to have the same terminal arm as negative 330. But add 360 again means it's going to have the same terminal arm as the angle 30 degrees. Okay, so that's where we're going to draw it. We'll talk about that again in a second, but we're going to leave some space and we're going to focus on the cosine of negative 690, which is also going to be the cosine of 30. And I'll again show you why that is in a second. So we said we'd end up at 30 degrees, which we know is closer to the x-axis in the first quadrant. So what is this negative 690? So all the way around once is negative 360. And then all the way around back to our terminal arm gives us our negative 690 degrees. But it makes alpha 30 degrees. All right, and our by the CAST rule, C-A-S-T, cos is positive here and here. So it's going to be positive cosine of 30. And the cosine of 30 degrees was right here. Cosine of 30 degrees is root 3 over 2. So it's going to be positive root 3 over 2. But we want the secant, so we're going to flip it upside down, 2 over root 3. All right, so let's check our answer. So to do that, we would have to do 1 divided by the cos of negative 690, which gives us 1.1547 positive, and then 2 divided by the square root of 3, also 1.154700. Okay, so our success criteria are that we can use the CAST rule and special triangles to determine the exact value of trig ratios, and understanding how to sketch angles that are larger than 360 as well as negative angles. All right, thank you.